Hey, Katie.
Hey, Ben.
So I am pretty excited about this episode. I don't think our listeners will realize the gravity of the situation until we actually start talking about our topic, which is gravity.
Gravity.
Yeah, so we're going to talk about gravity. You are listening to Linear Digressions. So, Katie, this episode is going to be a little more physics heavy because you are a crazy physics geek.
Well, are you saying that there's no direct application of gravitational waves in data science and machine learning? Is that what you're saying, Ben?
Gravitational waves.
Yeah,
It's
so
amazing.
this is the news out of science this week, and we're going to go off-piste a little bit to talk about it because it's just so cool. And I don't know, I think that our audience is people who are generally interested and curious and like science. So let's do it. So big week this week out of, I guess you would call it cosmology. There was the first direct detection of gravitational waves. So let me explain a little bit the background, I guess. So gravitational waves are something that were predicted by Albert Einstein's theory of general relativity. And in general, pun not intended, general relativity has a very good track record of giving us predictions that can be verified experimentally.
Right. Maybe not necessarily easily, but they have been.
Yeah, so general relativity is basically the idea that there's this thing called space-time, and that gravity is actually bends in space-time that are caused by large amounts of mass.
Yeah, a lot of the times you will see this demonstrated with like a flat sheet or a flat grid, and then you see planets creating these dips or valleys in space-time, and space-time is this grid. The reality is a little more three-dimensional than that, but that's a very good way of kind of visualizing it in a two-dimensional space, and then you can generalize that to a three-dimensional space.
Yeah, I always like to think of it as bowling balls on a trampoline, where you can imagine the trampoline you think of as flat until there's a bowling ball on it, and then as the bowling ball rolls around, it kind of like bends the curvature of the surface.
And if you start rolling a marble around in a circle around the bowling ball, because of the bend in the trampoline, the marble will actually orbit, quote unquote, the bowling ball.
Yeah, and there's a number of really interesting astronomical studies that have been showing us indirectly that this is the right way to think about it. So one major example is gravitational lensing from the presence of dark matter. So dark matter is material that, as far as we can tell, only interacts gravitationally. It also might interact via the weak nuclear force, and there are a lot of experiments that are trying to detect it via interactions with the nuclei of atoms. But the idea of dark matter is basically that it's matter. It doesn't interact with the electromagnetic force. That's why we call it dark, is that when you send light through dark matter, it doesn't reflect off of it, it doesn't get absorbed, it doesn't get re-emitted. Those are interactions that it just doesn't have with the electromagnetic force. However, it does have mass, and so it can create the bends in space-time the same way that regular matter does. And so what ends up happening is if you have a big blob of dark matter between you and, let's say, a big star, then the light from the star is traveling towards you. It bends around the dark matter, following the curvature of space-time. And so then when it reaches Earth, you end up seeing these arcs and kind of strange patterns in the light because of the gravitational lensing that we call it, that it goes through when it's actually traveling through space towards us.
Yeah, it's kind of amazing. I mean, you often will think about, or at least I often thought about gravity as something that interacted with like stuff. Like this pen that I'm holding right here is affected by gravity. But it's amazing to think that no, gravity actually affects even things like light, things that we don't think of as things.
Yeah. Well, I guess maybe the way to think about it is gravity affects the topology of space-time.
Right.
And light has to travel through space-time and therefore has to follow the bends in that topology.
Right. Yeah, that is a much better way of describing it. But it blew my mind when I first learned that and learned about gravitational lensing and the fact that everything is affected pretty much by gravity.
So gravitational lensing is an example of what we might think of as indirect detection. Einstein's theory of general relativity also predicts that when you have large changes in the amount of gravity, there can be certain types of cosmological events, for example, that can sort of send out waves in space-time, gravitational waves. So this is the example of, now I don't just have a bowling ball that's sitting in the middle of my trampoline, but I'm throwing a bowling ball onto my trampoline. And that's going to make sort of a vibration or a ripple that will then propagate through space-time.
And that's much easier to imagine if you imagine that the trampoline is like 100 feet wide. Then it'll definitely make a ripple. Whereas, maybe with a smaller trampoline, you could visualize it just going down, but because it's so small, you wouldn't necessarily see a ripple.
Yeah, yeah. And in fact, gravitational waves, gravitational ripples are predicted by general relativity, but gravity is very weak, and these ripples in space-time are very, very small. And so detecting them directly, as opposed to sort of looking at their effects on light or other kinds of phenomena, detecting them directly is a very tricky experimental measurement to make. But if you could directly observe them, it would be a type of smoking gun evidence for general relativity in a way that we haven't already seen.
You said if you can directly observe them, Katie.
Well, it's not if anymore. That was the big announcement this week.
This is so cool.
So there is a collaboration. It's called LIGO, Ligo.
All caps.
Yes.
I always read it in my head as if it's shouted.
Well, I think they're shouting this week. So LIGO is a direct detection gravitational wave observatory. And it's designed specifically to look for evidence of gravitational waves that are coming out of major cosmological events. So a good example of this is the event that they announced this week. They saw it back in September and have been analyzing and cross-checking the data for the last few months. But this particular event was two black holes spiraling into each other. And this creates apparently very large gravitational waves. And those were what LIGO detected.
One of my favorite things about reading about this announcement is I knew about LIGO, but I didn't actually know how it works. And so you imagine if a gravitational wave passes through Earth, then you can imagine that maybe Earth gets contracted in one dimension and expanded in another dimension, and then vice versa, contracted in that dimension and expanded in the other dimension. So it kind of vibrates along with the gravitational wave. And so in order to...
Can I just interrupt for a second?
Please.
It's, again, sort of like the correction I made you with, I made of the statement you made about light. It's not even that the Earth is expanding and contracting. It's that, that's kind of the effect, but space-time is, yeah. And so if you are measuring very precisely, where certain objects are on Earth, and then space-time actually contracts in between those two objects, then it looks like they're closer together. So that's what we're talking about here.
Right. And the effect is very, very, very small, like less than one atom of expansion or contraction.
Not just an atom, a proton.
Oh, less than one proton.
Yeah.
It's really, really small.
Yeah. So the way that they do this, it's kind of interesting. We'll talk about the way they do this, and then we can talk about black holes at the end.
Yeah.
The way that they do this is they have two experimental setups. One of them is in Louisiana, and the other is in Washington State.
And presumably that would be duplicated because if they detect something in one place, they want to make sure they detect it in another place in case it may be like a motorcycle passing and vibrating equipment or something weird like that.
Sure. Yeah, that local effects are not going to be showing up in both places at the same time. And the setups are, as far as I know, identical. It's kind of an L-shaped apparatus, and each leg of the L is 2.5 miles long. Inside this 2.5 mile long tunnel, basically, is a very empty vacuum. And then at the far end of the leg is a extremely high purity and very precise mirror. And so what happens is you have a laser that you send out.
And you send out the laser at the crook of the L in the middle.
So you send out a laser that looks like it's on track to sort of go along the bottom leg of the L. But you have a mirror right at the kink in the L that actually ends up splitting the laser beam. And so half of the beam gets sent up the up-down leg, and the other half goes along the left-right leg.
Left-right leg, yeah.
Yeah. reflects off the very high purity mirror. The wave comes back, and then the mirror that split it then recombines the two halves of the wave and sends them down into a detector that's sort of below, like, the bottom of the L, so to speak.
And so as the gravitational wave passes, when we were saying the difference is less than the width of the proton, the size of a proton, we're talking about this contraption, basically. This humongous detector gets squished, and not really squished, but the space-time it occupies gets squished or stretched less than that amount.
Yeah, so the idea is that when there's a gravitational wave that rolls past this thing, it's very precisely calibrated so that when both legs are exactly the same length, then when the two laser beams are recombined, they're going to cancel exactly. And so what you're going to see in the detector is just nothing. It's just electromagnetic waves canceling. And then if you have a gravitational wave that passes over this thing, the idea is that because you have two orthogonal distances, that one of them might get stretched and the other one stays the same length, or one of them might get squished and the other one gets stretched. Or the idea is that they're going to be changing, at least one of them, and not necessarily in exactly the same way. And so this very precise distance that they share, that they're exactly the same length, that no longer becomes true, that the distances aren't equal anymore. And when the distances aren't equal, then that means that the lasers that are traveling along them, one of them goes slightly further than the other one. And that means that then when they meet back up at the detector, they're no longer canceling perfectly, but there's a slight offset between the two electromagnetic waves. And so in your detector, instead of seeing nothing, you start to see a little bit of the laser. And so that's how they're able to make this very, very precise measurement, is by looking at for just little hints of the laser interference no longer working.
This is amazing to me for two reasons. First of all, it's, I think, a brilliant idea for determining whether one of the legs has, quote unquote, been lengthened or shortened in terms of the amount of distance that the laser beam has to travel. And secondly, that they were able to isolate this equipment from all of the other sources of noise enough. One of the articles that I read about this was saying that they were working about on isolating all of the equipment in all the different ways from all the different possible sources of noises, thunderstorms that are nearby, or sorry, I should say lightning storms that are nearby, motorcycles driving by, seismic variations, like all kinds of stuff. And they almost missed the signal because they were going to take the whole thing offline to do some calibration and some work on this or that. But had they done it, they would have actually missed the signal. So yeah, I'm just going to read a paragraph from this article. On Sunday, September 13th, Effler spent the day at the Livingston site with a colleague, finishing a battery of last-minute tests. Quote, we yelled, we vibrated things with shakers, we tapped on things, we introduced magnetic radiation, we did all kinds of things, she said. And of course, everything was taking longer than it was supposed to. At 4 a.m, with one test still left to do, a simulation of a truck driver hitting the brakes nearby, they decided to pack it in. They drove home, leaving the instrument to gather data in peace. The signal arrived not long after 4:50 a.m., 50 minutes later. Passing through the two detectors within 7 milliseconds of each other, it was 4 days before the start of Advanced LIGO's first official run. So, kind of unexpected that they're in the middle of, calibrating this device, and they decided to not do this final test and go home instead. And because they did that, and because they also didn't have the whole thing offline for other calibrations, some radio frequency interference they were trying to track down, that's the reason that they got this signal.
Yeah, they did get a little bit lucky on this one. So we should also talk about the scientific content of this discovery. So the first thing was, of course, they were able to verify that general relativity was right. Einstein was correct. I don't think anyone really doubted that, but you never know until you know. So that's always interesting to have a major theory like that directly confirmed for the first time. Mm-hmm. Second thing was, I think they now have a better understanding of things like black hole dynamics. So what was it that they actually saw when they made this measurement? So what they saw was two merging black holes. What happened was, this happens very frequently, that you can get binary star systems where you have two stars that are circling each other.
Yeah, isn't like a good proportion of the stars you see up in the sky are actually binary star systems where you have two stars orbiting each other?
Yep. And then those stars go through their regular stellar life cycles. And if they're big enough, the way that ends is that a star will become a black hole. And so what you can get from a binary star system is actually a binary black hole system where the two things that used to be stars are now burned out stars. They're black holes, but they're still circling each other the same way that they were during their lifetime.
Mm-hmm. And this is what we were looking at with this signal.
Well, what we
observed, I should say.
What we observed with the signal was not them actually circling each other, but it was them spiraling closer and closer and closer, and then they merge, right? It's kind of like they fall into each other.
That is incredible.
Yeah, it's really cool.
Crazy.
So it's these two black holes. They're 1.3 billion light years away. They're circling. And over the course of about a fifth of a second, they're speeding up. They're going something like half the speed of light once they finally get pulled into each other's gravitational orbit, like so closely that they just end up merging. And so you can imagine what that sounds like a little bit. You get the gravitational waves of their relatively slow precession around one another. And then as they're speeding up, the gravitational waves are becoming higher and higher frequency. And then they just stop all of a sudden as the two black holes, they stop spinning around each other because they're just one black hole now. They've merged. And so you can actually hear the sound. This is pretty cool.
And just because I'm a pedant in this way, this is not an actual sound of the black holes merging. This is taking the gravitational waves that we observed and converting them into sound so we can experience them in that way. But it's still pretty cool because you can kind of more intuitively understand the motion of the frequency of those waves.
And it's just fun to listen to. Like, it's a cute little noise. It's a kind of a chirp. Did you hear it?
Yeah, I did. And also the article says, if you haven't heard it, another thing that you can do if you have a piano is to use the back of your fingers and run them along the piano from the lowest A up to middle C. I wanted to go do that right now because I have a piano right here.
Yep, that's what it sounds like. That was really cool.
Yeah. So it's just this glissando, right? And so before the black holes actually merge, it's like whoa, 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 whoa. Very, very low, very difficult to hear with your ears, right? But it just accelerates and eventually whoop, does that thing.
Yep. The thing that I think we're also very excited about is that this is called an observatory. This is hopefully the first of many observations that this experimental apparatus will be able to make. Not just merging black holes, but many other types of astrophysical phenomena that could hypothetically have gravitational effects. And so I think the idea is that LIGO, with the sensitivity that it has and sort of some of the models that we have of how frequent these types of events might be and where they're distributed in the universe, the goal is that LIGO would be able to see tens of events like this per year. So we did get pretty lucky with respect to seeing this really lovely signal like right at the outset, but I think that there will be many more to come. So it's not just an issue of we get one of these and we're done, but it becomes something that we can really continue to study. As one of my friends at work pointed out, it's interesting because before we've only been able to study the universe by looking at it through observations of basically electromagnetic radiations. We look at
light, radio waves, infrared, etc.
Yeah. And for the first time, we're able to observe it using a different fundamental force of gravity. So the analogy is we've been able to see all along, but we've been deaf. And now with LIGO, we can see, but we can also hear. It's a fundamental new sense that we have, a fundamentally new way of observing the universe, and that is really cool.
Wow. And what a way to kick it off too.
Yeah.
To observe two black holes colliding. You said they were 1.3 billion light years away?
Mm-hmm.
So that means that this event took place 1.3 billion years ago.
And it's been traveling across the cosmos waiting to say hello to us.
This little chirp.
Yeah.
Linear Digressions is a Creative Commons endeavor, which means you can share or use it any way you like. Just tell them we said hi. To find out more about this or any other episode of Linear Digressions, go to lineardigressions.com. And if you like this podcast, go ahead and leave us a review on iTunes so other people get to listen to this content too. You can always get in touch with either of us. Our emails are ben@lineardigressions.com and katie@lineardigressions.com in case you have comments or suggestions for future shows. You can tweet us at lindigressions. Thank you for joining us, and we'll see you next time.